if you've got some source of sound, source in the sense of the thing creating the sound, like let's say a car that's honking its horn right now, and it's moving, let's say, to the left, then it has just created, let's say it has just created a crest. The crest is spreading out in all directions. So here's the crest, the crest of high pressure air that has just produced. If this was just staying still, the crests would be these concentric circles, or rather concentric spheres that are all at the same center point, all spreading out from the same source. But the source is moving. So the next crest out, the next wavefront, was created when the source was a little bit further over here. So it was spreading out from a different location. And the next larger one was created earlier when the source was even further back. So it's going to be more back here. And the next one is centered even further back. And so these circles, these expanding spheres of sound wave are not concentric anymore. They're not emanating from the same center. They're sort of offset because the source that created them has moved. Which means if you're standing over here, that is, if the source is moving away from you, what's going to be different about how you perceive this sound wave?
Is it the frequency of the sound waves?
Yeah, you're going to hear a different frequency. And it can be kind of difficult to see the frequency on the diagram like this because the physical distance from wavefront to wavefront, what do we call that distance?
Wavelength.
Right, the wavelength, lambda. And since the source is moving away from you, the wavelength gets spread out. So it's a larger wavelength. But a larger wavelength tells you what about the frequency?
Lower frequency?
Right, so you're going to hear a lower frequency. In other words, a lower pitch note. So the source is still producing the same note it always was. But if you're standing behind it, if you're standing in a position where it's traveling away from you, you hear a lower pitch note than what was actually being produced. That doesn't mean what you're hearing is incorrect. It just means you're hearing a note that has been modified by the motion of the source. On the other hand, if you're standing in front of the source, if the source is traveling towards you, what do you notice about this wavelength from crest to crest?
It's getting smaller, so it would have a higher frequency.
Exactly, a smaller wavelength, because the wavefronts are getting more bunched together by the motion of the source, means you hear a higher frequency. Which means if a car is driving towards you and passes you, you hear a change in frequency. You're going to hear a higher note as it's coming towards you, and then as soon as it passes you, from that point onward, you're hearing a lower note. And this is what produces the characteristic sound of something passing you by, because it's changing from Doppler shift making it a higher note to Doppler shift making it a lower note. Any questions on that so far?
No.
On the other hand, if you have a source, whether it's staying still or moving, and let's say you are now moving towards the source. If you, the observer, are moving towards the source, would you expect to hear the same frequency or higher or lower?
Higher?
Yeah, it should be higher. Even apart from the wavelength, if you're moving towards the source, you're going to be encountering more of these wave fronts per second. And frequency is all about number of cycles that hit your ears per second. So you're going to hear a higher frequency because you're intercepting more wave fronts per second. Or if you're moving away, it's going to take more time for each wavefront to catch up to you. So if you're moving away from the source, you're going to hear a lower frequency because you're going to be intercepted by fewer waves per second. So conceptually, I think that's what we should expect. If the source is moving towards the observer hears a higher frequency. Away from the observer hears a lower frequency. And as for the observer, if the observer is moving towards the source, the observer is going to hear a higher frequency. Away from the source, you hear a lower frequency. Any questions on that conceptually so far? So let's take a look at the equation involved here. The usual Doppler equation, the way it's usually written, is it's an equation describing how the frequency that's observed, usually written as F sub O, compares to the frequency that's created by the source. So this is saying the frequency that's heard by the observer, F sub observer, equals the frequency created by the source times a modifier fraction. And that modifier is typically written as V plus or minus V observer divided by V plus or minus V source. So VO and VS are the speed that the observer is traveling at and the speed that the source is traveling at. And then these frequencies are the frequency produced by source. And the frequency heard by the observer. And then this other V here without the subscript, what does this V represent?
Is that the speed of sound?
Yeah, the speed of sound. Or more generally, whatever wave we're talking about, because this same principle also applies to things like ripples in water. Like if you've got a moving boat and you're looking at the ripples it creates, and even light waves as well. Any sort of wave that's produced by a moving source and or being observed by a moving observer. So this V is the speed of the wave itself. Whatever type of wave we're dealing with. And this generally should apply to any Doppler effect situation. Anytime you have either a source that's moving as it produces the wave and or an observer that's moving as they observe the wave, then this equation can be used. Usually the tricky part is figuring out whether to use plus or minus here, and sometimes figuring out what's the source and what's the observer, but usually that's pretty clear based on what's creating the sound and who's listening to the sound. Usually the tricky things are figuring out what are your knowns versus unknowns. What do you know? What are you trying to find? Arranging it into this equation and deciding whether to use plus or minus. And what do you suppose the plus and minus represents here?
Does it represent if the observer is moving towards or away, and then if the source is moving towards or away?
Yeah, it's all about that direction of travel, towards or away from the other thing. And I find it's often difficult to try and remember general rules about whether plus means towards or minus means away or vice versa. So I usually look at it in terms of, based on the motion, should I expect this effect to increase or decrease the frequency? And then choose a plus or minus based on whether I expect an increase or decrease. And I think it's probably going to be best to investigate this by trying out some examples. So as one example, let's say we have, let's say a car in motion. And let's say it's moving to the right at V, and of course this will be V source if the car is creating noise. V source, let's say, is 20 meters per second. And let's say you are standing on the sidewalk nearby and walking the other direction away from the car, or walking away from the car. at, let's say, V observer equals, let's say, 5 meters per second. I guess maybe more running if it's 5 meters per second. So you've got a car that's traveling at 20 meters per second, and you're on the sidewalk nearby jogging at 5 meters per second. And you're listening to the car, and you hear the car honking at a frequency of, let's say, 800 hertz. And let's say we want to know what was the car's actual frequency. What sound was the car producing? Any questions on that general setup so far? So let's see how this would play into the Doppler equation itself. Of these terms, let's just list out all of the values. F observer, F source, V observer, V source, and V of the wave. Of these, what do we know? Do we have values for any of these?
We have VO, VS, and then
Yeah, we got those
we
speeds.
have the observer's frequency, right? Because that's the 800 hertz.
Right, what you hear is frequency of the observer. So you've got 800 hertz for the frequency of the observer. Do we know the frequency created by the source?
That's what we're solving for.
Yeah, that's unknown, so that's what we're trying to find. So all that's left is speed of the wave. And what type of wave are we talking about here?
A sound wave.
Right, and since it's sound in air, what's the usual typical speed for sound in air? How fast do we usually expect sound to travel?
Is it like 340, 300?
Yeah, generally somewhere between 340 and 350 meters per second. It depends on things like the temperature of the air, and I think the humidity also, like how dense other particles in the oxygen and nitrogen are. But let's say, just for making the numbers easier to work with, let's assume it's about 350. So 350 meters per second. I think in typical conditions, it's usually more like about 343, 345, something like that. But let's just say for now, it's 350 meters per second. At this point, we now know everything except frequency of the source. So we should be able to fill in all these values and solve for F source. Before we do though, let's see if we can figure out whether these should be plus or minus. First of all, based on, if we take a look at the numerator, V plus or minus speed of the observer, just looking at the observer's motion, you as the observer are moving away from the source. Would you expect that motion to create a higher or lower frequency if that was the only thing that was happening?
Lower.
Yeah, if you're moving away from the source, it's going to take more time for each crest to catch up with you. So we'd expect a lower frequency. The observer's motion suggests a lower frequency. So looking at just the numerator, because that's the only thing that has to do with the observer's motion. For the numerator, if we want the result to be lower, should we expect a larger or smaller numerator?
Small.
Yeah, we want a smaller numerator, and you achieve a smaller numerator by using plus or minus.
Minus.
Yeah, we're going to use minus to get a smaller numerator to create a lower frequency. Meanwhile, if we take a look at the car, the source is motion, the source is moving towards the observer. Does that suggest a higher or lower frequency being heard?
A higher frequency.
Right, because in front of the car, as the car moves, the waves are going to get bunched up. Shorter wavelength means higher frequency. So we should expect that the source's motion suggests a higher frequency. but the source's motion is involving the denominator. If we want the denominator to create a larger result, should the denominator be larger or smaller?
Larger.
A larger denominator, if you're dividing by a larger number, what happens to the result?
It gets smaller.
Right, but we want a higher frequency
wait.
result.
Okay, then a smaller denominator.
Right. We need a smaller denominator. Because a smaller denominator dividing by a smaller number means a larger result, which is what we want. So how do you make the denominator smaller, plus or minus?
Minus.
Yeah, so we should be using minus in the denominator as well. Use minus in the numerator to make the numerator smaller, to make the result smaller. And also use minus in the denominator to make the denominator smaller, which makes the result larger. Any questions on that so far? And if you want a general rule here, it looks like since these are both moving in the direction from the source towards the observer, and those both lead to minus, it looks like the direction from the source towards the observer is the negative direction in terms of choosing negative there. So if you do want a general rule, that should do it. And then likewise, the direction from the observer towards the source would be the plus direction. But I usually find it difficult to remember rules like that. I'm always going to forget it and try and remember, is it this way or that way? Is that plus or minus? So I generally just ignore rules like that and look at it in terms of, should I expect this to increase or decrease the result? Should I use plus or minus to make that happen? That I think is usually the best way to approach things like this. So that gives us the general formula. We have all the values except for frequency of the source. Any other questions on the setup of the equation so far? Then let's try running the numbers. We've got frequency of the observer, which we know, equals frequency of the source, which we don't, times this ratio of speed of sound in air minus speed of the observer over speed of sound in air minus speed of the source, the car. So 350 minus 5 would be 345. 350 minus 20 would be 330. And since the numerator and denominator are both in meters per second, the units cancel out, so we can just leave it as a unitless multiplier. And then how would we isolate Fs here?
Divide the fraction.
Yeah, divide both sides by that fraction, or in other words, multiply by its reciprocal. So frequency of the source should be 800 hertz, the frequency of the that's observed, modified by the reciprocal, 330 over 345. And those are both multiples of 3, so we can reduce that to 110 over 115. And further, those are both multiples of 5, so we can divide by 5 and reduce that to 22 over 23. So it looks like the frequency of the source is 22/23 of the 800 hertz. So 22 over 23 times 800 hertz.
About 765.
765, thank you. So 765 hertz would be the sound that's actually being produced by the car's horn. And you hear a higher sound, even though you're moving away from the car, which would suggest a lower sound, but the car is moving towards you even faster. So that overwhelms it, and overall you get a higher sound than what this car is actually producing. Any questions on that so far?
So based on like the original setup of the problem, we can expect like what the overall result would be. It's just that the
Yeah.
car going faster.
Right, based on the motion of the source and the motion of the observer, I would use that to predict conceptually, should you expect a higher or lower result from each piece individually. Like we found from the overall result that the sound of the observer, sound heard by the observer is overall higher than the sound produced by the source. But in terms of setting up the equation, I would look at it one piece at a time. Like if the observer is moving away, if you imagine that was the only thing happening, would that cause a higher or lower effect? And the car is moving towards the observer, if that was the only thing happening, would that create a higher or lower frequency? So look at each motion individually to choose the pluses or minuses, and then work from there. Any other questions on that?
No.
All right. Or any other questions on Doppler effect in general? Then let's take a look at interference as well, since that's another big topic that's going to be returned to many times over the next few weeks. What do you know about interference so far? Like what has to be happening to create interference?
Two waves have to meet.
Yeah, you got to have two waves. They got to be interfacing with each other, essentially two waves occupying the same space. And it could be more than two waves. You could possibly have many waves occupying the same space at the same time, interfering to create one overall effect. But currently, we're just going to look at two waves occupying the same space. And that typically means either you've got two sources, like maybe you've got two speakers that are both creating sound in the same room. Or maybe you've got one source creating sound and also it's hitting a wall and echoing back. So you might have a wave and its own echo interfering with each other. That essentially counts as two waves in the same space, even though one is just the echo of the other. The important thing is they're going in opposite directions. So the outgoing wave acts like a wave created by the speaker, and the echo acts like another wave created by the wall. Or alternatively, you might have, maybe you've got one speaker creating sound, but you've got a wall with two holes in it. The sound gets through both holes, and you can treat each hole in the wall as a source, and the sound from one hole and the sound from the other hole interfere with each other as well. So that's usually called double slit interference, and that's also going to be an example we look into in great detail. But in general, as long as you've got sound or any wave, sound or ripples in water or light coming from two sources and occupying the same space, then that creates interference. And it might help to look at this visually in terms of the graphs. Like let's say we have a graph of position versus displacement. And you've got one wave that looks like this at a certain instant in time. And then let's say you've got another wave that looks like this. Each one of those waves, maybe from two different sources, is trying to create some sort of effect on the air, if we assume these are sound waves. You could treat Y essentially as the pressure in air at that location in space. So at this point, wave one is trying to create high pressure, and wave two is also trying to create high pressure. If you've got two different phenomena that are both trying to create high pressure, what's actually going to happen to the air pressure at that point?
You would get a higher pressure.
Yeah, you're going to get very high pressure. Essentially, these values, these Y values add together, the displacements add. So the actual result is going to be very high pressure here. And likewise, at this location in space, wave one is trying to create low pressure, wave two is also trying to create low pressure. So what really happens there?
You would get a lower pressure.
Yeah, you get even lower pressure. The Y values add together. A negative plus a negative equals an even larger negative. What about at this location? What's the value of each wave here?
They're both 0.
Right. So if you take 0 plus another 0, it's still going to be 0. Again, we are essentially just adding together the y values of both waves at each location. At this location, likewise, we've also got 0 plus another 0, so it's still 0. Here we've got a large positive plus another large positive. So a positive plus a positive gives you an even larger positive. 0 plus 0 is still 0. A negative plus another negative is a larger negative. 0 plus, pretty close to 0 is 0. Positive plus positive is even larger positive. So overall, we still get oscillations. It's just going to be much larger oscillations. And you don't really, if you're listening to these, you don't really hear both waves individually. You just hear the overall result. And the overall result is going to be, looks like the same frequency, since both of these waves had the same frequency anyway. But what has changed about this wave?
Amplitude.
Right, this is a larger amplitude. If this is sound, what does a larger amplitude mean for sound? What would you observe?
Louder.
Yeah, it's going to be louder. So the two waves together, since you've got crest and crest lining up to create a bigger crest, trough and trough lining up to create a bigger trough, you would hear a loud sound. Usually we would refer to this as maximum loudness or maximum amplitude. And we would call this constructive interference. Constructive in the sense that the waves are combining together to create an even stronger overall wave, an overall effect that's stronger, in this case, louder. Or if we were talking about light, what does amplitude mean for light? What would you observe if the light had very large amplitude?
The brightness.
Yeah, it's going to be very bright. Not bright in the sense of color, but bright in the sense of like how shiny it is, I guess you might say, how much energy is hitting your eyes per second. So very bright light or very loud sound, or if these are like ripples in water, they would be very large ripples, lots of displacement. So that would be constructive interference. If you got crest and crest lining up, trough and trough lining up to create an even larger crest, even larger trough. On the other hand, if you had them lining up oppositely, like let's say you have one wave that looks like this, and one wave that looks like this. In that case, if you have crest and trough lining up, you've got a positive plus a negative. So what's that going to be?
0.
Yeah. And then equilibrium and equilibrium, that's 0 plus 0, so that's also 0. And here, a negative and a positive, that adds up to 0. 0 and 0 is 0, and so on. So in this case, you just get a flat line. If this was sound, what would you hear?
Nothing.
Yeah, this would just be silence. This would be two sound waves that cancel out, because one of the waves at a certain point is trying to create a high pressure zone. The other is simultaneously trying to create a low pressure zone that adds up to no change in pressure at all. You just get atmospheric pressure the whole time, so you'd hear no sound at all, if it's truly completely destructive. Or if it's light, this would be a dark zone. There's no light at all. I mean, there's certainly two sources trying to create light there, but they cancel out, so you get a dark spot. And this doesn't actually happen very often. It's very rare to get completely destructive interference. I mean, technically it is still called destructive interference, but that really only becomes completely a dead zone if the amplitudes completely cancel out. Often what's much more likely is if you've got, let's say, one wave with a large amplitude and another wave that's interfering destructively but has a smaller amplitude. Something like this. And let me actually draw in the x-axis here. In a case like that, here we've got a large positive plus a small negative. So what do we get if we add those together?
A smaller positive.
Yeah, they don't completely cancel out. We get a little bit of positive left. And likewise, here we've got a large negative plus a small positive. So what does that become?
A smaller negative.
Right. So we do get some oscillation here. It's just going to be much weaker. So the actual wave you would hear or see, whatever type of wave it is going to be something, but it's not going to be very much. And this would still be called destructive interference, in the sense that the waves have canceled out as much as they possibly can. But it's not going to be completely deadened out. It's not going to be truly zero, because they're not going to cancel out unless they're the same amplitude. They're just canceling out as much as they can. So destructive interference can mean complete silence or completely dark if the waves that are interfering with each other destructively have the same amplitude. If they've got different amplitudes, then there is still going to be a final resulting wave. It's just going to be much weaker, but not completely zero. It's still called destructive interference, though. Any questions on that so far? So constructive interference, if crest and crest line up and trough line up perfectly. Destructive interference, if you've got crest of one wave and trough of the other lining up perfectly, and vice versa. There's also an in-between case, if you have crests and troughs not quite lining up either way. For example, this one ends up always being a lot more difficult to draw. So let's say you have one wave that looks like this, and another wave, let's say it has an equilibrium here and then a crest, equilibrium, trough, something like this. In that case, the crests don't line up with the crests and the troughs don't line up with the troughs. So it's not going to be truly constructive. It's not going to be truly destructive either. We can still use the same approach of adding together the y values. Here we've got 0 plus this value is just this value. Kind of high plus kind of high equals a little bit higher. And then 0 plus this value is this value. 0 plus this value is this value. And then kind of low plus kind of low is adding up to something like this. 0 plus a negative is that negative. Then I guess we're going to pass through 0 when we have the same amount of up and down. Those average out to 0. Then 0 plus a positive is a positive. Kind of positive plus kind of positive is more positive, and then 0 plus a positive, and so on. So we do get oscillations. It's definitely not destructive because the resulting wave is not deadened out. It's also not constructive though, because it's not as large an amplitude as it could be. If the crests truly matched up, this would be a much higher amplitude. They don't. So we do get a slightly higher amplitude, but not very much higher. So this, in a situation like that, where it's neither constructive nor destructive, but somewhere in between, would be called partial interference. We sometimes categorize that, like if it's pretty close to crest and crest lining up, like in this case, I think I would call that mostly constructive interference. Or if it's pretty close to trough and crest lining up, so they almost cancel out, I would call that mostly destructive interference. But in general, if you don't have crest truly lining up with another crest or another trough, if it's somewhere in between, you would call that just partial interference. Any questions on that so far? So let's see how it would actually calculate how that works. Let's say you've got two waves, let's say sound waves coming from speakers, and one of them looks like this. For simplicity, let's assume the other one is the same frequency, but it's just coming from a different location. So maybe it's traveling further to get to your ears or not traveling as far. If it's traveling in a way such that it lines up precisely, what kind of interference is that?
Constructive.
Yeah, that's going to be constructive. We got crest and crest creating a larger crest, trough and trough creating a larger trough. So that would be constructive. If the waves are absolutely identical, no difference at all. But let's say we shift one of them. Maybe one of them didn't have to travel as far, so it's got a head start. If we take that wave and shift it a certain distance forward, So let's say they're starting the same way. They're both starting at equilibrium on the way up, but one of them has a head start in space. Now, what kind of interference is that?
Destructive.
Yeah, destructive interference. And in order to get that, if you consider their starting points, let's assume this is an x-axis. So we've got like an x versus y graph. What's the extra head start? How far ahead did one of them have to start in order to get that effect?
A full wavelength or like a full period?
Is that, well, we're talking about x versus y rather than t versus y. So we would be talking about wavelength.
Got
It
it.
isn't a full wavelength though. It's just from equilibrium to crest equilibrium.
Oh, so it's half, right?
Right, that's half of a wavelength. If they're offset by exactly half of a cycle, then that means it's destructive interference. But let's say we shift it a little further. Let's say instead of shifting half a cycle, let's say we shift one full cycle. So we have, again, starting from equilibrium on the way up, but let's shift that forward one full cycle from here to here. So equilibrium on the way up. Now for the original purple wave and this new green wave, what kind of interference are these now creating?
Constructive.
Yeah, that's constructive interference as a result of how much difference in starting point? How far of a head start did the green wave get?
A full wavelength.
Yeah, one full wavelength. And that head start we typically call delta x. Delta x just meaning the difference in path length, because x represent, if you go back to the original sine wave equation, the sine of 2 pi over period times t plus or minus 2 pi over wavelength times x. In that equation, x represents how far the wave has traveled to get to the observer's location. So delta x means the difference in how far the waves are traveling. Let's say you're standing over here listening. One of the waves started here and traveled to your location. So that would be, let's say we call that distance x1. The other wave got a bit of a head start. It started here and traveled this far to get to your location. So x1 and x2 represent the path length, how far the waves travel to get to your location. The extra distance traveled by one of them is the path length difference, delta x. And of course, these don't have to be collinear with each other. They don't have to be parallel. You might have something like, here's a speaker, here's another speaker, and you're standing here. In that case, your path lengths would be this distance and this distance. And then delta x would be this length minus this length. And you could subtract x1 minus x2 or x2 minus x1, just make sure you're consistent about it. So that's called the path length difference.
Wait, so for the waves, when you drew out like the x1 and x2 on the top, is that just the difference from like wave or the starting point?
Yeah, like if we assume that these waves are created by speakers, let's say we've got a speaker here that's creating a wave. And let's say there's another speaker here that's creating another wave. So that represents where the wave starts. That's the source that creates the wave. If the sources are in different locations, then the waves have to travel different distances to get to your ears. And they might be traveling a very, very long way, but how far they travel doesn't really matter. All that matters is the extra distance traveled by the one that's traveling a little bit longer. So for instance, if one of them is traveling 100 meters and the other one's traveling 100.5 meters, the important thing is the extra 0.5 meters traveled, because that's where you get a difference in what type of point of the wave you're at, whether it's a crest or a trough or whatever. And so far, we've seen that if that difference in path length is half of a wavelength, you get destructive interference, crest and trough, trough and crest and trough. But if that difference is a whole wavelength, then they match up. Crest and crest match up, trough and trough match up. What if we made it a little longer? What if we moved the speakers again and they were now, let's say, 2 whole wavelengths apart from each other? What sort of interference would you expect if delta x is 2 wavelengths?
Constructive.
Constructive. And why is that?
Because it's like it's just a multiple of like a single wavelength, right?
Yeah, exactly. 1 full wavelength means we've taken a crest and shifted it so it overlaps with the next crest. If we shifted 2 wavelengths, it would overlap with a crest further down, but the crest would still overlap with another crest. In general, if the only thing you're doing is changing the path length, but you change it by a whole number of cycles, that crest still lines up with another crest further down the line. So in general, and this is assuming that the path length difference is the only difference. There could be other things changing. Maybe they're different frequencies. Maybe their phases are out of phase, their sources are out of phase. But in general, if the path length is the only difference, then delta x being a whole number of wavelengths and just representing some whole number, then we get constructive interference. Whereas what has to happen in order to create destructive interference?
You would need if the delta x is n/2 wavelengths.
Sort of, but we got to be careful about the notation there, because n/2 could still be a whole number. For instance, if n is 6, 6/2 would be 3, and 3 wavelengths would still be constructive.
It would be like n multiplier times the wavelength over 2.
That's still just going to be n times wavelength over, if we just have n times wavelength over 2, that still runs into problems if n is like, let's say 4. 4 lambda over 2 would still be 2 wavelengths, which is constructive. What are you trying to say conceptually though? Without messing around with the equations, what sort of distances give you destructive interference? Like for instance, half of lambda works. What would be the next one that creates destructive interference?
3/2.
Yeah, 3/2 lambda would also be destructive. What else?
5/2.
5/2 lambda.
So it would be like something plus some number to make like an odd number over 2.
Yeah, one way to write this is odd number over 2 times lambda. And a very useful way of writing any odd number. Well, first of all, how could you write any even number? How could you create what's guaranteed to be an even number?
Is 2n.
Yeah, 2n is guaranteed to be an even number. How do you modify that to make it an odd number?
2n plus 1.
Yeah, 2n plus 1. So that's guaranteed to be an odd number divided by 2 times wavelength. So 2n plus 1, guaranteed to be an odd number, divided by 2 times the wavelength. We could also split that up. 2n/2, which is just n, plus 1/2 times the wavelength. So this is also a useful way to write that. N plus 1/2, that is something and a half wavelengths. So 1.5 or 2.5 or 3.5 or 4.5. In general, if delta x is something and a half wavelengths, that's going to be destructive interference. And then anything in between would be partial interference. So for instance, if the difference in path length was like 5 1/3 wavelengths or 7.2 wavelengths, anything other than a whole number of wavelengths or something and a half wavelengths, anything else is going to be partial interference. But these are generally the important things to look for. If the path length is the only difference between the waves, no other differences, like same frequency, same phase, same everything else. If the difference in path length is a whole number of wavelengths, including 0, then you get constructive interference guaranteed. If the difference in path length is something and a half wavelengths exactly, that's always going to be destructive interference. And then anything in between would be partial. Any other questions on that?
No, thank you.
You're welcome. So try applying that to some examples. Keep in mind that these general rules only apply if x is the only difference, if there's no other differences between the sources. But we can look into how those differences influence it next time. So I will see you later.
Thank you.
You're welcome.